Hi, I'm Jeha Kim with Seoul National University, and it is my great pleasure to give you an introduction to silicon photonic systems and their modeling with XMODEL. Silicon photonic systems integrate both photonic and electronic components on the same chip, and they are very promising in realizing dense, high bandwidth IOs that dissipate low power. This dense IO bandwidth can be achieved through a technique called wavelength division multiplexing, which enables a transmission of multiple data streams through a single fiber. Through this technique, if you pack 8 streams of 12.5 gigabit per second, you can achieve a total of 100 gigabit per second data stream, data bandwidth through a single fiber channel. That is extremely high density that you cannot achieve with any other solution, including the electrical links. This slide shows a typical configuration of a silicon photonics I/O transceiver. First, you have a laser source that could be either external or within the same system, and it generates a laser that propagates through a waveguide. That laser, the intensity of that laser can be modulated through a various means, for example, a micro ring modulator, or maybe a Moss gender modulator. We'll talk about that later, based on, depending on the digital data that you want to transmit. So at the end, after the modulator, you have this laser signal whose intensity is changing over time depending on the data. Now that laser, that optical signal propagates through the optical fiber to the receiver chip. At the receiver side, you use some sort of a optical filter that will select the particular wavelength that you want to listen to. And then you monitor, you convert the intensity of that particular wavelength optical signal back to an electrical signal, typically using a photodetector. And by doing this, you have a transmitter and receiver. And as I said, you can have multiple wavelengths propagating through the same waveguide. Therefore, you can achieve a very high bandwidth, high density I/O. That's a promise that silicon photonics I/O has. So what's the big deal about silicon photonics system? What's the difficulty or challenge in designing or verifying these systems? Well, the first difficulty starts with these photonic components. It's not just the photonic components is little different from the other electrical components within the chip. It's the signal that they propagate. It's extremely high frequency, like a few hundreds terahertz. And that's not it. They have to interface with analog mixed signal circuit operating at tens of gigahertz. Of course, you need high precision in simulating them because they're analog. But both photonic and analog, they're kind of sensitive to environment, for example, temperature. So you need some sort of calibration loop that is typically done through a digital feedback loop. And the digital circuits have a large number of transistors, therefore they're complex. And simulating this complex digital system working with a high precision analog, also interfacing with a photonics element propagating at an extremely high frequency is an impossible task, right? And now you have to verify that this whole system, having photonic, analog, and digital, is working correctly together. That's the challenge. So how are we going to address this? Our goal is to model the silicon photonic system in System Verilog. Basically, we want to run efficient simulation, including silicon photonics, analog, and digital electronics, all in System Verilog. So you may ask, why System Verilog? Because it is the established platform for verifying most of the chips today. Of course, I'm talking about the digital chips. which takes the majority of the chips that we're building today. And the advantage is that if you could do this, after the validation, after the verification, you can take the digital models and synthesize them. You know, that's the way we build digital chips today, right? So now the question is, how do we deal with analog and photonics? Fortunately, there's a tool called XMODEL, which offers a set of primitives for modeling silicon photonics as well as analog, all in system Verilog. And when it comes to photonic simulation, it enables two things. First, it enables event-driven simulation with full optical wave signals. Second, it supports bidirectional signal propagation and reflection. We'll see what these means in the next few slides. So let me give you a brief introduction to what XMODEL is. It's a tool developed by Scientific Analog, and it's basically a plugin extension that enables analog mixed signal simulation in system Verilog. It has a very unique event-driven algorithm that delivers a very fast speed compared to real number Verilog. And when it supports analog simulation, it not only supports functional model simulation, like just describing what the analog circuit does, but if it is required, you can model the analog circuits directly. What I mean by that is you can just draw transistors, resistors, and just connect them together to describe a circuit within system Verilog. And I'm not talking about SPICE here. And of course, by doing this, everything can be simulated within system Verilog, and we can achieve our goal. So let's start looking at the basic problem with simulating optical signal. The problem stems from the fact that the optical signal that we're using in the silicon photonics system has extremely high frequency. For example, the laser with 1550 nanometer wavelength has 192 terahertz frequency. So expressing this signal naively within system Verilog using a set of points like this will just trigger too many events and slow down the simulation unbearably, right? Unbearably slow, right? Of course, no one does that. And there is a smart way that people have been using, which is called baseband equivalent method. The assumption is that we're assuming that the optical signal has a fixed standard frequency. Like think of a carrier frequency in an RF. And what's really changing is this complex amplitude multiplied with the sinusoid, which either express amplitude and phase, or you may say the in phase and quarter to phase components of this amplitude. And by doing so, you can dramatically reduce the amount of events required to express the signal, because even though the signal itself may be extremely high frequency, but if you take this carrier frequency component out, the remaining term, this C of t term, can vary at a much slower rate. That means that it will require much less events within the system Verilog simulation. Therefore, we can go faster. Well, what XMODEL does in comparison is that it uses a functional expression rather than a set of points to describe these continuous time waveform. And I will go a little bit in detail in the next slide. But for now, you can see that it uses a functional expression, which is basically a sum of exponential function. And you know that, well, exponential function can express sinusoids. Since you can combine multiple sinusoids through the summation, and you can use these coefficient in front of each of the exponential, it's possible to have a much fewer events describe the same signal. And not only that, if you consider this wavelength division multiplexing system, you have multiple carrier frequencies. Expressing those signals extremely difficult with the baseband equivalent because you're assuming a one fixed carrier frequency. But within the XMODEL functional expression, it's readily available because you can express a sum of multiple sinusoids. Well, this is the key idea behind XMODEL, which uses these functional model to describe a continuous time waveform. And once you express your signal using this functional expression, you can do the simulation of your system or circuit in an event-driven manner. The key is you take this functional expression of the signal and do a Laplace transform, which results in a sum of these partial fractions. Now, once you have your signal expressed in Laplace domain, computing the response of a given system that has a transfer function is very simple. You just take the product between the two, right? So you take the product between these two Laplace domain expression, do a partial fraction decomposition, you get this sum of partial fractions again, which is the same form as the original input expression, which means that now we can take this expression and compute this response of next system, and so on. And the key thing is that this computation only needs to be done once when the input expression is updated, which means you only compute the output when there's a change at the input. That is event-driven. So XMODEL has extended this technique to optical wave simulations, the photonic simulation, which means that even when you have these 200 terahertz optical signal, you can still do this very efficient event-driven simulation and achieve and perform a very fast simulation. So what you're seeing here is digital data modulating the intensity of the optical signal. And at the receiver side, that's being converted back to the electrical signal through photo detection. Let's zoom in a little bit more. For the optical signal, you still cannot see the waveform because it's extremely high frequency. But what you see on the markers that you see over there indicate where the events are being triggered during the system, during the system Verilog simulation. What you see is that it's purely event-driven. What I mean by that is when the input data changes from 0 to 1, that triggers an event, and that event triggers an event on the optical signal, which in turn triggers the event on the received signal. And when the data goes back to 0, that triggers the one event in the optical signal and another event in the received signal. No event happens between those two events. So even when the optical signal has extremely high frequency, this simulation is just triggering 2 events for each signal. Of course, it's fast. So the other challenge that you address is that when the laser, these optical signals propagate through a media like a waveguide, they can propagate in both directions, like forward and backward. And this is what really happens in real systems. And when the wave gets to one end of the waveguide, they may get reflected depending on what's on the end of the waveguide. Okay, and all of these are not a typical phenomenon modeled by system Verilog, which models a system that propagates signal in only one direction. So how do you do this? Well, luckily, XMODEL, it has a capability of modeling circuits, which is kind of like, like we model circuits. So it can simulate a system that has a notion of voltage and currents. And you can do so easily by just expressing the circuits directly using what's called circuit primitives. For instance, let's say you have a circuit that's made of these set of switches and capacitor. Depending on how you modeled it, it could be tricky in modeling in their switching behavior. In that case, you can simply list those switches and capacitor in this system Verilog syntax as if you're listing the SPICE netlist. And this will work within system Verilog. And you'll get the analog behavior as if you're doing the same thing in SPICE. So XMODEL can do this. And as one of the circuit primitive, XMODEL offers transmission line. It's called T-line. And this T-line primitives has all the right thing to model an optical waveguides that propagate these laser in both direction and has these reflections depending on the end conditions. For instance, it can model a propagation delay between the ports, and depending on the difference in the characteristic impedance at these endpoints, it can reflect waves. And as the wave propagates through the transmission line, this primitive can model a frequency-dependent losses through the transfer function notation. So we'll see that XMODEL will use this T-line for modeling various optical waveguides and their derivatives. So for instance, XMODEL offers primitives for modeling the basic photonic elements, such as laser source, waveguide, phase shifter, directional coupler, photodetector, and terminations. We'll look at each of these elements in more detail in later slides. But what you notice is that they all have some part described as a waveguide. So they all propagate optical wave in two directions, and they will reflect if the one waveguide changes to another with different refraction index. And using these basic photonic primitives, you can combine them to build various composite elements that are used in silicon photonic systems. Those include a ring resonator, modulator, and ring filters. And you can also model Mach-Zehnder interferometers, electro-absorption modulators, and so on. Again, we'll talk about these elements in more detail in later slides. Sometimes it's more efficient to model some of these composite elements directly. So XMODEL offers a primitive for these composite elements, such as ring resonator, ring modulator, and ring filter. And these primitives achieve faster speed because the way these ring modulators work, ring resonators work, is that when there's an incident wave propagating through, depending on the condition, it can be trapped within the ring, and that wave will just keep propagating within the ring. And let's say that happens, then for a system Verilog simulation perspective, it means that every time the wave goes around the loop, you'll have an event propagating to the output, because that's going to cause something at the output. And that means that for a single event coming in, you have multiple events being generated, being propagated to the output. That's not so good for simulation efficiency. So these primitives model the same behavior without causing a large number of events at the output. So I talked about these primitives. So if you want to model photonics, analog, and digital all in the same simulation platform, we not only need a primitive for photonics element, but also we need for analog. Well, digital is already there for system Verilog, right? So there are 7 more categories of primitives XMODEL. Just to walk you through what they are. Some of them are for modeling timing circuits, like converting between clock and their properties. There are a set of primitives for modeling this various stimulus. These are useful for when building test benches. And there are primitives for modeling precise digital gates with precise timing. And then, well, since we are dealing with both analog and digital, of course, and optical, sometimes we have to convert between them. So there are primitive for connecting those two types of signals. Well, we're doing verification on this photonic systems. That means we must be able to measure some characteristics and see if that's satisfactory or not. So there are a set of measurement primitives. And finally, XMODEL offers a set of primitives for modeling various circuit elements like transistor, resistor, capacitor, and the T-line, the transmission line, is one of them too. And finally, there's a set of primitives for modeling what the circuit does, like what are the functions of the circuit, like adding and multiplying, filtering, integrating, transitioning into from digital to analog and vice versa, sampling, delaying, and so on. Okay, so what you see is that in XMODEL, you never write codes to model your systems or circuit. You just put together these XMODEL primitives as a building blocks. And that means if you, and furthermore, if you use a tool called Glister, you don't have to write codes at all. You can just build the models in a schematic form, and you can simulate from the schematic directly. So to give you an idea, here's some example, the simplest example of a wavelength division multiplexing link using these XMODEL primitive. This is a Cadence Virtuoso schematic editor, and Glister offers the XMODEL primitives as a set of symbols. So modeling in this environment is simply placing these primitive symbols on the schematic and connecting them up. Right? So you see here the primitive for the laser source, ring modulator, photodetector. Those are the silicon photonic primitives. And on the transmitter side, you see a clock triggering a PRBS generator, which gets transitioned into an analog signal, modulating the ring modulator. And on the receive side, this photodetector will convert the incoming optical signal into a current. It's called photocurrent. And then when that current flows into a resistant capacitor, you get a voltage output. Okay. And within this environment, you can simply generate the system variable netlist using the Glister feature, where you see a system variable module that has a set of signals being used within the model, and a set of primitives that are placed on the schematic, and some extra commands for dumping the waveforms. And you can run simulation within system Verilog, such as Cadence NC Verilog, Synopsys VCS, along with these XMODEL engine. Okay. So, well, seeing is believing. So why don't I show you an actual demo on this? Okay. So this is the example that I just explained. It has a laser source. Laser is being modulated by the transmit data, which is converted back to electrical signal through this photodetector. To generate the system Verilog netlist, the model from the schematic, you click this Generate XMODEL netlist menu. It says the netlist is done. You can see the model being generated, which is what I just explained. And run the simulation here is simply pressing this Run XMODEL Simulation button. Okay. So it's happening here. Simulation finished within like 3 seconds. Let's pull up the waveform. And here's a source. Okay, let me just click them first. Source, modulated optical signal, and the received signal. And let's see this digital data we're sending to. Okay. All right. So this, maybe this should place right here. So first we're sending a continuous wave laser, which is like a fixed frequency sinusoid. So I have to zoom in a lot to see its actual sinusoidal because it's like, again, 200 terahertz signal. And depending on this digital data, this ring modulator changes the amplitude of the optical signal. So sometimes you have an optical wave propagating, sometimes it's being blocked. And when it gets to the photodetector, it will generate a signal, the current, which is proportional to the intensity of the laser, incoming laser. And when that current flows through the resistor and capacitor, you see this voltage going up and down. So what you see is that data is being correctly propagated to the receive side, right? And if I do this, you see the event markers. And like I said before, you see there are very few events being triggered, despite the fact that we're simulating an extremely high frequency signal, right? And this is how this simulation could be finished within 3 seconds. Okay. All right, so from now on, I'd like to review the elements of silicon photonics system and how they correspond to XMODEL primitives. Okay. Here's a picture of a typical silicon photonics system that has a laser source, some sort of modulator, and the modulator signal gets coupled onto a waveguide between the transmitter and receiver. On the receive side, you select a certain wavelength you want to listen to, and then you detect that signal and convert that into an electric signal through a photodetector. So you see a lot of elements here, like waveguide, modulator, photodetector, and so on. So let's talk about those. So starting with optical waves, it's essentially an electromagnetic wave that can propagate in free space. And when the light propagates in free space, they travel at a speed of 300,000 kilometers per second. Right? Of course, the speed changes as the light travels through a different medium than the free space. And typically, it slows down, right? And the factor that it slows down is commonly referred to refraction index. So the speed of light within that medium with a refraction index of n is c naught, which is the speed of light within free space, divided by n. And from the physics, we know that we can express the speed of a wave, the propagation velocity of wave, can be expressed as a product between the frequency of the wave and the wavelength of the wave. Well, since optical signal is basically a propagating wave, we can express that using a wave equation. So a wave equation has basically maybe 2 components or 3 components. Well, one component is the magnitude, the amplitude information. The second term expresses how this wave changes as a function of position. And the last term here is how the wave changes as a function of time. And we see these 2 coefficients, k and omega. Using these coefficients, we can define a various property like velocity and delay. And there are 2 kinds of definition for velocity. For example, there's a phase velocity, which is defined as a direct ratio between omega and k, and group velocity, which is the derivative of omega with respect to k. And you can find a lot of material talk about the difference between the 2. Well, phase velocity is basically a velocity of a wave at a single frequency. And it doesn't necessarily carry information. But on the other hand, group velocity is not just a single frequency wave. It's more like a collection of waves centered around a given frequency. So with those a like group of waves that have slightly different frequency, you can propagate information. So this group velocity is actually the speed at which the information propagates. Okay. So based on these two different velocity definition, you can also have a two different definition for refraction index, which are called effective index and group index, as well as delays, phase delay and group delay. They're all derived from the phase velocity and group velocity, respectively. Okay. So velocity describes how fast these waves propagate through the medium. And most medium will have a different propagation velocity depending on the frequency of the signal, you may say, or the wavelength of the signal. Okay, so that's some non-ideality that you may have to take into account. And the other non-ideality is that not many waveguides are lossless. Well, they have a very low loss compared to the electrical channel, but still there can be a non-zero losses. That means this amplitude information, A of X, may be attenuating as you propagate a longer distance. So that's the wave equation, and typically we are interested in the intensity of the optical signal, which is defined as the average power flow per unit area at a given point. So that intensity is a cross product between the electrical field intensity and the magnetic field intensity, which is sometimes called Poynting vector. And it gives you actually the power intensity, because it gives you amount of power at a single point, amount of power per area at a single point. So if you want to see the total power that your waveguide is propagating, you have to take the area integration of that intensity information, which is called optical power. So it's basically the average power flow across the total area. Okay, now that we talked about optical signal, let's talk about the source that generates that, optical signal. Well, there's various laser sources we can use in silicon photonics system, and they generate coherent light. Basically the light that has a stable frequency and phase. Most laser source will give you the light at a fixed wavelength and maybe variable power at certain level of power. Some laser sources may generate multiple wavelengths as well. Okay, and a silicon photonics system, sometimes these laser sources are external. They're generated using more traditional method, and they're coupled onto the chip, the silicon photonics chip, through a fiber. Or sometimes you may bond these hybrid laser source onto the silicon substrate. If you want to model this continuous time laser source in an XMODEL, you can use this CW laser primitive, and it has a set of parameters to model different kinds of laser sources. For example, you can describe a set of wavelength it is generating, power being generated for each wavelength, and if you care, you can also specify the initial phase for these optical signals. Now that you have generated optical signal, they must propagate within the silicon photonics chips. Most silicon photonics chip that people are using today are based on silicon on insulator substrate. It's because, the silicon on SOI substrate has this silicon top layer on top of this insulator layer, which is oxide. And this is where people build like transistors and so on. And silicon photonics people use this technology rather than the bulk technology to build silicon photonics. the main reason is by having this oxide layer underneath the silicon top, you can easily build a silicon-based wire that are totally surrounded by the oxide, right? So by doing this, you can basically build a fiber. This is how you build a fiber. You confine a low refraction index material with a high refraction index material. That way, once the light wave is coupled within the standard material, it gets confined through a mechanism called total internal refraction, right? So the light gets confined there. The only way it can go is along this waveguide. There are some details about the waveguide. For example, in general, the waveguide can propagate multiple modes of light. But to avoid complexity, most optical waveguide used for silicon photonics system, they're designed to support only one mode, for example, TE mode. And in general, like I said, they can be dispersive, like having different velocity depending on the wavelength. They can be lossy, and they may have a different propagation characteristic depending on the polarization of the optical signal. So these are some details that if you want to have a really high precision silicon photonic systems. In XMODEL, it models these optical waveguide using the transmission line primitive, the T-line primitive internally, and model the optical signal as a set of equivalent voltage and current waves. Okay, well, yeah, and that means the power, the total power being propagated through the waveguides can be calculated by taking the product between the voltage and current. Well, there are two things that we need to talk about the waveguide. One is called, optical path length, or in short, OPL. And this describes how long the waveguide is. Okay. You may be familiar with the concept of electrical length in electrical wire, like transmission line, which describes the length of a transmission line not using its physical length, but using the propagation delay. We say, oh, this transmission line is 10 seconds long, 2 seconds long, or and so on. Similarly, optical path length basically uses the same information, the delay that the light takes to propagate through the waveguide, but it translates into a distance that the light will propagate in free space in the same amount of time. Okay, this is just to avoid some confusion, due to the different refraction index of different material, and this is pretty standard for photonics people. So please get used to this. One little hazy topic is characteristic impedance. Waveguide, it's a medium that propagates energy, and if the endpoint cannot fully absorb the energy or propagate to another direction, the energy will have to bounce back, which will cause reflection. Okay, and the best way to describe the reflection behavior is to use a concept called characteristic impedance. And this is very closely related to the refraction index of these waveguides. Okay, but the thing is that I don't think there is a good consensus on how to derive characteristic impedance for a optical waveguide. There are a lot of literature on it, but they all have a slightly different opinion on how to do this. And one difficulty stems from the fact that you cannot really define voltage and current for waveguides because they are not orthogonal. There's a technical way of saying that is that there's no TEM mode being supported. But just to take it as there's no established way of defining character impedance. But turns out that we don't really need to define them accurately because we don't really care about what the absolute value of this characteristic impedance is, because to describe the reflection behavior, all we care is the ratio. Let's say you have two waveguides being connected. The reflection behavior depends only on the ratio between the characteristic impedance of these two waveguides. So no matter how you define it, as long as you define it in a consistent way, it will give you the same ratio. With using the other method, um, you know, as long as you're consistent and give the right ratio between these character impedance, you're fine. Yeah. All right. Next element to talk about is a photodetector, which is the device that converts the optical power into an electric current. In silicon photonics system, the most common device is essentially a PN junction in a depletion mode. Like you put PN junction in a reverse bias at the interface of the PN junction, you get an area called depletion region where you have very few number of electron holes. And you use that because when the light hits that region, it will generate the electron hole pairs, and that will generate current. Okay. The key characteristic that describes the photodetector is called responsivity. It describes how much current will be produced by the photodetector when a unit power of optical signal shines on the surface of the photodetector. Okay. There are some other characteristics, including the bandwidth of the photodetector, dark current, which kind of describes how much noise it is generating, even when the light is not shining the photodetector and so on. But those are kind of small details. To model photodetector in XMODEL, there is pH detector primitive. Of course, you can describe the responsivity as a parameter, which can also be a function of the optical wavelength. Okay, and since the optical signal shining the photodetector will be propagated through the waveguide, it has extra parameter for, let's say, the characteristics impedance. All right. If you put two optical waveguides and put them close enough to each other so that they can be coupled, you get a structure called optical directional couplers. So this is basically two coupled waveguides that can exchange energy. And if you go deeper, through this, within this coupled region, the incident energy will be split into what's called even mode and odd mode. And these two different modes will have two different propagation velocity that gives you a different amount of distribution of energy depending on the position along this coupled region. But long story short, the end characteristic is that when there is the incident wave with a certain intensity, a fraction of that will just propagate through. So this tau is the amount of energy propagating, just keep propagating the same waveguide. And some other energy will propagate to the other side. Okay, and so this coefficient kappa is describing how much energy will get to the other side. And what's interesting is through this interaction between the even mode and odd mode, this wave reaching on the other side of the waveguide is always shifted by minus 90 degrees. And there's no energy going back into this point. Okay. So the corresponding XMODEL primitive is called Dirac coupler, directional coupler, and it has two parameters, gain through and gain couple, that correspond to kappa and tau, respectively. And these coefficients must specify this condition because the total energy has to be conserved, or After the propagation, the total energy has to be less than the incident energy because this structure cannot generate energy by itself. Okay, there is a parameter called phase coupling, which means it describes the additional phase shift between the in and couple ports. Of course, the default is minus 90 degree, but you can change it if you want. A similar structure to this directional coupler is optical Y branch. It is named after its shape. It has a single port on one side and 2 ports on the other side. And this is a structure that can either split or combine optical powers. For instance, if the light is coming from this side, from the left, then as it propagates through, the incoming light will be split into 2 outputs. Okay, so some portion will go to one port and the other portion will go to the other port. And if it's totally symmetric, you'll see half even split between the 2 ports. If the light is propagating in the other direction, then you can use the same structure as a power combiner. Yeah, so there is a corresponding XMODEL primitive, which is called Y branch, and it's basically described by, the gain between the incident port and the through port. One small primitive is modeling the terminator. So this is a structure that's not, I don't think there's a clear element that people use in silicon photonics system, but you need to have a clear concept about this. For example, if you just leave the waveguide open end, then theoretically the energy that propagate that end can bounce back. And of course, well, depending on the situation, you may want it or may not want it. And if you don't want it, you have to make sure that that end has a impedance matched to the characteristic impedance of the waveguide so that the reflection cannot happen. For example, you can put some damping structure that can absorb the optical energy. Sometimes you do want reflection. And typically when you do that, when you want reflection, you say, I want a mirror there, right? You put a mirror structure that will reflect light. So that corresponds to having like a 0 or infinite characteristic impedance at the end. All right, so far, most of the elements that I talked about were kind of passive, like they have a fixed characteristics that does something. But if you want to transmit information from the transmitter to the receiver, we have to change something, right? And that change will propagate as information. So one useful device is called phase shifter, which is a device that can modulate the propagation delay through a medium. And this is done by changing the refraction index of that medium. So there are various different ways, and one very popular way is to use an effect called plasma dispersion effects, which is the phenomenon where the refraction index of the silicon material changes with the density of the electrons and holes of the material of the silicon. So earlier I talked about depletion region. So by changing the amount of reverse bias, you can change how depleted your PN junction is. That will change the carrier density. Therefore, you can modulate the refraction index. Right? So here's a cross-section of a typical silicon-based phase shifter where you have a PN junction and each side is connected to metal, so you can apply reverse bias to it. And depending on the amount of reverse bias, the depletion region that's formed across this boundary between the P and N will change, and that will modulate the overall carrier density of this whole area, and therefore the refraction index. okay? And when you change the refraction index of that part, it will change the propagation delay uh, of the light propagating through, okay? One thing to remember is that, well, the carrier density is a strong function of the temperature. It's like exponential function. So it's very sensitive to temperature. So later we'll see that many silicon photonic elements will have to be tuned to compensate this temperature variation. Okay, well, despite the fact that there's a complex mechanism behind the phase shifter, modeling it in the X model is pretty easy. There is a component called primitive called pH shifter, which has it as a one additional input to the waveguide structure, which just directly sets the delay through this waveguide. Okay, and you can also, by adding some other primitive over here, you can modulate that delay as a function of some other input. All right. Now, when you combine a waveguide with a ring, which is another waveguide, you can form a ring resonator. Another way of looking at this is that there is a waveguide being coupled to this ring-shaped waveguide. So it's kind of two sets of waveguide with a directional coupler coupling the two. Okay? So most of the time, the incident wave coming on this waveguide will just propagate through. But for a particular wavelength, the wavelength that will satisfy the resonant condition, that means if the optical path length of this ring is the integer multiple of the wavelength, then it means that the optical wave propagating this ring can sustain itself. So that's basically a resonance. In that case, all the energy, the energy of the incident wave can be trapped within the ring and doesn't get out, right? So from the outside point of view, it looks like you're blocking the propagation. And of course, you can make this the resonant condition tunable by changing the delay around this ring. For example, using a phase shifter. The transfer function from the input port and output port of the resonator is a band stop filter because it blocks the propagation of light only for a certain wavelength. And it turns out those wavelength is not a single value, it's multiple value. So you see this band stop filter with the periodically spaced resonant frequencies, and the spacing between two adjacent resonant frequency or two notches is called free spectral range. And if you look at one of the notches closer, you can see how selective that band stop filter is. And just like in any resonant filter, this full width and half maximum is determined by the resonant factor, the Q factor of this filter, which is the function of these parameter. Well, I didn't describe that. So, well, this is basically a directional coupler. So there is a coefficient to describe how much is propagating through, how much being coupled onto the other side. And there's additional parameter describing the propagation delay around the loop, which is going to call T ring. And this alpha, which describes the loss of this ring when the wave propagates around it. Okay, and this Q factor, which determines the full width at half maximum, as well as the free spectral range, they are the function of these parameters. There is a ring res primitive X model, which describes the optical ring resonator with essentially the same parameter, same set of parameter that I just described. You can easily build a ring modulator by placing a phase shifter as part of the ring, because that way you can change uh, the delay around this ring and therefore the resonant condition. Okay, so this ring res var primitive indicates that it's a ring resonator with the variable delay around the ring. So it has one additional parameter describing how much that delay is changing. You can couple more of this ring and waveguide to build more interesting structure, and one of them is called ring filter. So here we have two straight waveguides and a couple through this ring-shaped waveguides. So this part is basically a ring resonator, which means that when there's incident light, particular wavelength can be satisfying the resonant condition can be trapped within the ring. Once this ring has some energy within it, some of them can be coupled onto this second waveguide, straight waveguide on the other side. So this structure called ring filter because this structure can select one particular wavelength of the light from the incident and propagate to the other waveguide. Oops, yeah. And again, you can make this ring part variable, tunable by adding a phase shifter into it, which means that you can change the wavelength that you're selecting. So this ring filter, if you look at the transfer function from the input port to the through port, that's the band stop filter because it's basically a ring resonator. But if you look at the transfer function to in port to a drop port, then it's a band pass filter because it will only select a certain wavelength and propagate that to the drop port. So you have kind of the opposite transfer function for those two port pairs, but they share the same free spectral range because they all get determined by the ring resonance condition, and they also have the same full width at half maximum value, basically the same Q factor. All right, so in XMODEL, there is a ring filter primitive that models this ring filter with the same set of parameter. There are more parameter because there are two directional couplers. One is coupling between the first straight waveguide with the ring, and the other one that's coupling between the ring and the second straight line. So there's tau 1, kappa 1, tau 2, kappa 2. Yeah, and when you make this ring delay variable, you get a ring modulator filter or ring resonator filter, and you have additional parameter on how that delay is changing. All right. Now let's switch gear to a different kind of modulator. The structure shown on this slide is called Mach-Zehnder modulator, or in short MZM. And this is another device that can modulate the transfer function between input port and the through port, depending on some control voltage. And it's made of two Y branches. The first one is acting as a splitter. The second one is acting as a combiner. The way it works is that you take the input laser, input light, split it into two paths. If these two paths have the same length or have the same propagation delay, after they get combined, they have the same phase, and you get the same in the original signal back because they add up. But if you modulate the propagation delay on one of the paths so that the phase of these signals become different, and in certain condition, let's say these phases are totally opposite, then when you combine them, they can subtract each other and cancel each other, and you get nothing out, right? So similar to the ring modulator case, in some condition, you may have a total propagation of the input power to the through port. In some other condition, you may get zero propagation. Okay, just that the mechanism of achieving that variable transfer function is different. Okay, so now that we have looked at some of the basic elements that makes a silicon photonic system, now let's see some simple examples on how to model some typical silicon photonic systems, namely the silicon photonic transceivers. So we have taken a look at a single channel wavelength division multiplexing link based on the ring modulator. So this time let's look at like 5-channel WDM links. So a way of doing that is you have a laser source that can generate 5 different wavelengths. These are the numbers. And each wavelength are modulated by the different ring modulator that are receiving, 5 independent digital channels. So you can do this because each modulator is just modulating the one particular wavelength that corresponds to the resonant condition of this ring. And for other wavelength, it will just propagate. Okay. So just putting them in series, you can individually modulate these different wavelengths of the optical signal. And when they propagate to the receive side, on the receive side, you use the ring filter to select one particular wavelength that you want to listen to. And then you take that into a photodetector to convert that into an electrical signal. Well, you can simulate this in XMODEL, and this is a simulated waveform. For 2 nanosecond simulation, it takes about 15 seconds, still very fast. This is the final transmit output that has the information of all the 5 channels. Of course, it's not easy to tell which one's which, but yeah, and these are the individual optical signals that are selected by the ring filter. Okay. And if you compare the transmitted signal, like those on the top, and the received signal, if you look carefully, you can see that they're basically identical. So this 5-channel wavelength division multiplexing link is working correctly, and the simulation is done very efficiently, even with these extremely high frequency optical signal containing multiple wavelengths. Okay. And we briefly talked about Mach-Zehnder modulator. And if you want to model that in XMODEL, you can use directional coupler. Well, you could use Y branch, but this example uses directional coupler, which does the same thing. And then one path is just a waveguide with a fixed propagation delay. The other path is another waveguide, but has a phase shifter, includes a phase shifter. That means that you can modulate its delay. And depending on this additional delay, these 2 waves may add up when you combine them back, or they could cancel each other. Okay. And if you want to build a transceiver pair, on the transmitter side, you have a laser source, which is being modulated by this Mach-Zehnder modulator based on the digital data. On the receive side, you have a photodetector converting the optical signal to the voltage, the current and the voltage. Right, this is a simulated waveform. The digital data modulate the optical signal through the Mach-Zehnder modulator, and the photodetector recovers the original waveform. So polarity is flipped, but you can see that other than that, the information is being propagated correctly between the transmitter and the receiver. And the simulation takes only 2.2 seconds for a 10 nanosecond simulation time. I didn't describe this, but well, there is another element that people consider using. It's called electro-absorption modulator. This is a special device that can modulate the band gap of the semiconductor by modulating the electric field. So as you know, if the incoming light energy matches the band gap, The electron can jump from the valence band to the conduction band, basically absorbing the energy. So by changing the band gap, you can change the wavelength of the light that this material is absorbing. Okay, and you can use that as a modulator. Okay? And this briefly describes how to model them. And here we're basically modeling the absorption through with a two setup transmission line with a variable resistor in between. Well, modeling a electro absorption modulated base link is fairly simple. It's very similar to the other links as well. Like you have a laser source, have a modulator, and this output will be modulated based on digital data. And once that feeds into a photodetector, you can recover the original signal. So here's the waveform, which takes 1.3 seconds for 10 nanosecond simulation. And again, you can see that the data is being propagated correctly, and the optical signals is simulated in full wave. Okay, so far, the examples were rather simple. Like you have a simple electrical components generating the transmit data, which then modulates some photonic component to change the intensity optical signal. On the receive side, you use the photodetector and additional electrical components to recover the electrical signal, the data in the electrical signal. But none of these really address the challenge that I mentioned earlier. So let's talk about a system that has a high level of integration between the photonics and electronic system, electronic components. This is an example that was published in JSSC 2016 by Dr. Chen Sun. He is a graduate at UC Berkeley, and he's now a CTO at IR Lab. And in his work, he described a thermal tuner for a ring resonator modulator. It's because of the reason that the resonant condition, the resonant frequency of the ring modulator is highly sensitive to temperature. It is necessary to monitor the resonant frequency and adjust the temperature if necessary. Okay. So what you do, in the system, what he does is that there is a continuous light coming in to this ring modulator, and you modulate the ring resonator with a training pattern, like that. It will have a it's like a PRBS pattern that has equal ones and zeros, and then you use the filter structure to tap some of the energy being modulated and monitor it with a photodetector. And you convert that into a digital information through an ADC and look at the separation between the 1 level and the 0 level and see how good of a separation you can get. If it's good, then you're in good condition. If it's not, then maybe it means that you have to make some adjustment to the resonant frequency to get to recover the good separation. And the means of doing that in this work is to change the temperature, like basically embedding a heater, like a resistive element near the ring resonator, and drive a different amount of current to adjust the temperature. Okay, so here's a big feedback loop that includes the photonic element, analog mixed signal element, as well as the digital feedback loop. Okay. This is a top level schematic of the actual model that we have implemented based on the description on that paper. Again, it includes the part for the modeling the photonic element, the analog element, and the digital element. And everything is described in system Verilog. Like the digital part is described in the pure plain system Verilog, the Verilog codes. The analog parts and the photonics are described using the XMODEL primitives. Here's a simulation waveform that basically explains the operation of this thermal tuner. What it does is, at the first phase, it will just sweep through a different temperature setting. From here to about around 6 microsecond, it will sweep through different temperature setting, and while feeding these training pattern. So during that period, you're changing the temperature and see how much of a separation between the 1 level and 0 level you get. You can see that as you sweep the temperature, the separation gradually changes, and at some point you hit the maximum, and then the separation gets smaller again. And you record all these results, and remember when you got the peak separation. So when the sweeping is done, you select the temperature that gave you the largest separation and start using it. And after that, you can start sending real data. Okay. So this simulation includes extremely high frequency optical signal propagating through the ring resonator, the analog circuits, the model for the analog circuits, they're doing the A to D conversion, as well as the D to A conversion when you are driving the heater, as well as driving the ring resonator. And then you have this massive digital circuits doing this complex sweeping, recording, and selections, and so on. So all of those took only about 2 minutes for 8.1 microsecond simulation time. Yeah. So you can see that we have achieved the goal. And this is the eye diagram before and after the calibration. So before, when the temperature is off, so the resonance is not at the right place, you basically have no separation at all. You cannot distinguish between 1 and 0. But after the calibration, now you have a good separation and have a clean eye in the middle. All right, so that's it. So in this tutorial, we have reviewed the basic elements of silicon photonics system and demonstrated how you can model them in XMODEL. And the example that we discussed includes the ring modulator based WDM links, Mach Zehnder based, and the electro absorption modulator based links. And as a final example that integrate both photonic, analog, and digital components, I discussed the example of modeling a thermal tuner for micro ring resonator. So maybe you felt a little odd that I talked about system Verilog and XMODEL all of a sudden, but it is currently the only solution that can model photonics and electronics all together in a single simulation platform while delivering a very fast speed with this full wave information. And I'd like to remind you that this is due to its unique signal representation that enables event-driven algorithm. Okay. And I'll look forward to answering your questions, and I hope you enjoyed this tutorial. Thank you.